Hello. I want to make a proper video about Minesweeper probabilities for a while, since I think my previous video was kind of bad, or maybe it wasn't. I didn't really check, but here I'm just gonna. I'm gonna try to make a better video, going through the whole thing. It's what I said, but it's probably gonna be just as bad. So we'll see. So first of all, let's just look at this this left thing here, this left board. Like, let's just cut everything out here, ignore everything. Here we just have a board, and what we want to do is we want to find the shore lines. I don't want to actually remove these, so I will just use a brush to draw this out. So what you first want to do, if you want to find the probabilities, you have to guess here. You don't know where any of the mines or safe spots are. This is a situation where you have to guess. So first of all, there's 10 mines, so that'll come up later. So keep that in mind. Not right now. We don't need that right now. So what we need to do is we need to divide these blocks, all of these blocks, right, into two types. We want the stuff that are adjacent to numbers, like this. So if there's a number here, then anything that's right next to those numbers, those are those blocks we want to find. Also, kind of make this a bit smaller. So this is all adjacent to numbers, right? And all of this is adjacent to numbers. So the rest of them, this and everything here, is not adjacent to numbers. So I should probably use a different color for that, like black, I guess, because I'm lazy. Yes, these two. This is how we divide it, right? If I were to actually draw lines between the blocks, kind of like that, it would look like this, I guess. I mean, you can always see on the right side that I colored that in. Colored the blocks that are adjacent to numbers are colored in. The blocks that are not adjacent to numbers are not colored in some different color. So these lines that end up being created are called shorelines. That's what I call them, because they just look like shores, while these are lands. So my motive is that they look like islands. You got an island here and you got an island here, I guess. This one doesn't have shorelines because it's like completely blocked off by these mines, but this one's do. And shorelines are what causes Minesweeper to become extremely complicated. Especially what do you call them, variable shorelines. There's no example of constant shorelines, so I won't go into that in this video. But basically, if there's both of these have an exact number of mines, both of these have a variable amount of mines in them. Like the left one has, let's see, there's one mine here, there's one mine here, and there is, since there's one mine here and one mine here, so there's 4 mines in this whole thing, right? And we know where 2 of the mines are, so there's 2 mines left, and that's here. So we know 1, 2, 3, 4, and there might be a 5th one, or there might not be. So there's I wrote this down here. There's 4 to 5 mines, or yeah, just 4 to 5 mines. The other one here, there's 2 mines here, because there's 1 mine, 2 mines, 3 mines, and there's 5 mines total. So there's okay, there's 2 mines here, right? And we know there's 1 mine here, so there could be 3 mines, or there could be another mine here. Like, let me give an example. There could be 2 mines here, 1 mine here, and in this situation, there has to be 1 mine among these, right? So this is 4 mines. In another situation, there could be 1 mine here, 1 mine here, 3 mines like that. So the shorelines are how should I put it? So the shorelines could have a multiple amount of mines. Like they could, like some shores actually have like just 1 mine amount, like 1 or 2, but all the shorelines here all have they'll have various amount of mine amounts. So these shorelines, I divided them into 2 like this, red ones and blue ones. And that's because they're connected to each other like that, and the probabilities change depending on each other. I'll just for now I'll just describe how to decide. Like, if we look at this 1, or no, let's look at this 2. It's the same thing, but this 2, we group every single block that is around that 2, and there's just 2 blocks surrounding that 2, and then we look at all the blocks that surround this 4, and there's these 4 blocks. So these overlap, like even at least one block overlaps between them, then they become connected and become a shoreline. And among like surrounding this 5, there's just these 2 blocks, right? So they just surround, they link in that way. So it's pretty easy so far. You just that's how you link these individual shores together to create a shoreline. So there's a few things we need to figure out about the board before we begin the calculations. What is there? So first of all, obviously I mentioned this thing. There's 10 mines, and we need to know how many mines there are in these shorelines. And you just kind of do that manually, or you just do it how I just showed you. I guess I just showed you how to do it. But here I draw I draw blue and green lines, kind of for every single hint that each number gives. Like this this blue one shows that there's 1 mine among these 2 blocks. The green one says exactly the same thing, so you just got redundant hints, I guess. Those happen very often in Minesweeper. The 4 shows that there's 2 mines among these 4, so the green is obviously 2, blue is 1, and you just got this whole thing going on. And same goes for this thing. You might wonder how I found this, how there's 1 mine among those 2 blocks. Let's see if I can show that. I will color these. Red is a mine and green is not a mine. So with these, if this is a mine, then you know this is not a mine, and this is a mine, and this is not a mine. So this part becomes green. If this is safe, then this is a mine, this is safe, and this is a mine. So this is like a kind of a logic statement, I guess. If there's 1 mine here, and there's 1 mine here, 1 mine here, then like this becomes like connected, I guess, and there's only a set amount of mines among those these 2 blocks. This is a common formation called a box, so this was easy for me, but there are more complex formations where even I like can't figure some things out. So, but anyway, we know that there's 4 to 5 mines on the left thing here. I need to just keep using this box here, and there's 4 to 3 mines here. So we figure that out. Total, we know that there is 9 to 7 mines, and that's what I wrote here. S means shore. This S means shore, and there's 9 to 7. And since there's 10 blocks here, I should use green. Okay. Since there's 10 blocks here, just subtract 10 from this, and you just get 1 to 3 mines among the land blocks. The L means land, which is all this stuff, right? These 2, the uncolored blocks. And finally, the most important part. Well, not the most important part, but just as important is we need to know how many land blocks are there. Right now, there's not that many, but you can imagine that there could be a ton of land blocks for a half unfinished Minesweeper board. So yeah, we know that there's 11 land blocks. I counted it. You can count it too right now, but you don't have to. So first thing I want to do, there's a simple thing that I can do, but I'm just gonna go with the complex part first. So for each mine amount here, 5 and 4, and for the right side 4 and 3, I find how many combinations there are for that. To figure that out, I just make the. I found out what condition needs to be met for for there to be 5 mines or 4 mines. So this one, there is 3 combinations, because you just take a look at the biggest I guess the biggest part of the shoreline, so the biggest one shore, you know. And there's 3 combinations in this. I need to use this box thing more often because it's more visible than this stupid thing that you can't even see. So there's 3 combinations here that affect all the probabilities here too, and there's 3 combinations here too. So you just get a 3 and 3, but in the parentheses I just show that I simplify it to 1 1, you know. And that'll be important because this will simplify a hell lot later on. And on the right side, there's 4 mines here. There's only 1 combination here. This is the only combination where there's 4 mines. Every other combination there's 3 mines. So 1 and 3. Now you take that and let's put it into down here. I would box this like this. Yeah, this is kind of important. This is, I would call it the identity of the board, I guess. This is all you need to know to find the whole probability of the entire board. So we're using this to find everything, right? That is, let's see. So the 1 1 and 1 3, right? I put it in here. Let me go back here for a second. So there's 1 1 here, and there's 1 3 here, and I put them into this shape, I guess, kind of like an array. Ignore this one for a second. We don't need that right now. We won't need this part for a very long time. So where was I now? Alright, so you want to consider these as polynomials, this each part, right? So this would be x plus 1, and this would be x plus 3, and you multiply them together to get x squared plus 4x plus 3. I'll just write that down, I guess. But that would only make things more complex for you, so I wouldn't just do that. So you got this, and we just multiply them like this, equals x squared plus 4x plus 3. Let me just drag this. There we go. Now I can see. So you have like 1 here, 1, 4, and 3. So that's what I'm looking for here. And this thing is just the inverse. So that is I don't know what to call it. The opposite polynomial, I guess. So these are just shoreline polynomials, individual shorelines, and this is the total polynomial, the total shoreline polynomial, I guess is what I call it. And this is what this is. Let's see if I can describe this right. So this divided by this. Let me get the text box here. Well, that's yeah, I hope that's good enough. Equals 1 3, you know. X plus 3. Here this is pretty simple. It's really just this and this. But when there's more than 2 polynomials, this would definitely get way more complex. But yeah, that's what we need to use. And then next, oh, this looks confusing. I really need to write this down in a better way. So Pascal ratios: 1, 5, 15. I'll describe how I found this out because none of this should be on the board right now. So we found the ratios of how many combinations there are for how many mines there are in each of these shorelines, and we found a total, right? Next we need to find is the land combinations, I guess. The land combinations. The amount of land combinations for each amount of mines. That is 1 to 3. Do I have the box thing here? Yeah. 1 to 3. So, how many combinations are there? There is 1 mine in 11 land blocks. There is 11 combinations that way. So, write that down. 11. Next, you want to find how many there are if there's 2 mines in 11 land blocks. That's 55. And then the next one is 165. Why I call this Pascal ratio is because this is just let's see if I can do this. 11 choose. Oh, I'm dumb. 11 choose 1. 11. Oh my god. 2 and 11 choose 3. Okay. I'm bad at typing. We got that through. So this is really just the operation that I'm doing. It's just combinations. And the way to find this is you just go into Pascal's numbers, Pascal's triangle, and what was the 10th thing? You know, the one that goes like this. You know that one? 1 3 3 1. That is each number is the addition of the top 2 numbers like that. So I think I'll show you a bit more. 1 4 6 4 1 1 5 10 10 1 5 1. Oh god. How do I? Okay, I can't do the spacing now because the numbers became 2 digits and stuff. Oh, great. I don't know, something like this. Okay, well, now I'm bad at triangles. That's what. So if you keep going down, you get to the 11th row. The first, second, and third number of the 11th row is these numbers. But I went with 1 5 15 because you can divide all of these by 11. I'll just write here. Divide by 11. And this is also important because in most boards, these Pascal numbers become incredibly large. They become like 100 digits. That's the largest I've seen. So in this simple simple example, you won't see something like that. But in some like 100 digits, yeah, you wanna simplify them, and they become like 20 digits from what I've seen. It's really convenient. So you don't want to look for like those really large numbers and then try to divide them all. Here's how you do it. You don't do any of this this operation like here. You just take that out. I'll show you a better way to find them. It's so we have numbers A, B, and C, I think, right? So A equals some number I don't know. B equals, we know what B equals, and that is in comparison to A, that is, how did it go? 11 minus 1 divided by 1. Was that right? No, divided by 2. Multiplied by A. No. So it's like this. A multiplied by 11. Subtract the first number, that is 1. Most of the time 1 is not the first number, but here it is. And then you divide it by the next number, you know. And then C equals B multiplied by 11 minus 2 divided by 3. So here you see 1, 2, 3 in the L mines. All come up here. Is that 1 and 2, and then you just add 1 to both of these numbers until the second number becomes the largest number, which right here is 3. And then A becomes the smallest number possible that is that does not make any of A, B, or C into anything but a whole number, you know? So A should be, what should it be? It could be 6, right? But if you were to simplify this, let me simplify these. 10 divided by 2 and 9 divided by 3, right? Well, that just simplifies to these. So A could just become 1. A can just equal 1, then B would equal 5, and then C would equals 5 times 3, so it would just become 15. And that's what we got here, 1, 5, 15. And so that's the ratios we got here. So we have two ratios. We have the shoreline combination ratios, and we have the land ratios, which is the number of combinations compared to each amount of mines. That is, if there's 1 landmine, if there's 2 landmines, and if there's 3 landmines. It's like that. So we multiply them both. Kind of I don't know what the operation was called now, but you just multiply 1 by 1, and you multiply 4 by 5, and you multiply 3 by 15, and you get this. This is the total combination. It's going to be the most important number in this whole thing. 66. That's what we get. We get 66. If you were to add all these together, I mean 45 plus 20 plus 1 becomes 66, right? So yeah, that's what we got. So first of all, let's solve the risk, the probability of dying if we were to click a land block, right? Just any of these land blocks. All land blocks, since we have no hints for them, they end up having the same exact amount of possibility of dying to them, like the same possibility of having a mine, that is, because like we know the mine amount, we know how many mines there are in the shores, the range of it. I mean, there's 9 to 7 mines, and we know that there's 1 to 3 mines in these blocks. So you think it'll be obvious, and you can just have an average, just 2 mines, right? But each amount of mines have a different amount of combinations, you know. So the land 1, 4, 3 affects the chance of the amount of landmines by that amount, and the amount of combinations by themselves, the Pascal numbers. That is, if there's 1 mine here, there's 11 combinations. If there's 3 mines here, there's 15 combinations. 3 mines in 11 blocks, you know. And so the simplest way to do this, we take the total combinations and you multiply the number of mines to each of them. That is, we get this, and then we just add them all together and we get 176, and then we divide this by the total combinations right here, and we get the average number of mines. And you just, so it's larger than 2. We thought it was 2, but it's larger than 2, obviously, because the larger the number, the more likely, the more combinations there are, meaning it's more likely to happen. So we got this, and you know, we just divide it by 11 and we just get this. So that's like 8 divided by 3 divided by 11, which is like 8 divided by 33. So it should get this, 24.242. So we're kind of like done with all the landmines. We know the probability of those. The problem is, most of the time land blocks are not the answer to a click. They usually have a low chance, a decently low chance, but not enough that you want to risk it. Especially because land blocks have a low yield, which is something I'll go into very soon. Land blocks don't. If you click one, you're not likely to solve the whole board. You know, if you were to click this, then your chance of like solving this part or this part, it's really low. You don't. Just not even worth the low risk that they have. And the biggest part is that their risk is really high compared to like any one of these shorelines, because they have variable variable probabilities. So the smallest probability of any of these blocks is almost always lower. Almost? No, they're most of the time they're always lower than the land block. Sorry, that doesn't make any sense. I'll just say most of the time because I just remembered a possibility where every single block is more likely to have a mine than the land block. It does happen. So next we need to find the shoreline what do you call that? Probabilities. So what I did here is what I do. So I take this. Let me take that. Let me move this here, right? Where should I put this? I'll just leave this like here, I guess. Yeah, that would be good. Alright, so what I did is I did a polynomial multiplication that is with 1 1 with 1 5 and then 1 1 with 5 15. And I multiply by 3. 66 16 15. Oh, that's not right. This is where the inverse comes in. Right here I get this inverse. Not the inverse. The inverse of a polynomial is a different definition. I have the opposite polynomial here for each shoreline. So I move that to here with a 1 3 here and 1 1 here. And I multiply this by putting the first number, 16, I get by multiplying this by 1, and then multiplying this by 3, and then adding them together. So 1 plus 15 equals 16. And then I do the same for the other two, is 5 plus 15 times 3. So that's 45 plus 5, that's 50. And after you do that, you need to double check and make sure that the total of these two numbers, is 66. The same goes for here. So 1 plus 5 equals 6, and then 5 plus 15 equals 20. As this is a 1 3, you multiply these by these, and you get 6 plus 6 60, and you get this number, of course. And then the next numbers, what are they? I just divide them by 2. This is, you don't have to simplify here. Now the complicated part is done. You all the parts where I told you to simplify is just for this total combination. Like once the total combination is as small as possible, the rest can't be more complex than the total combination amount, you know. But if you're doing this by hand, which I also don't recommend, then you want to divide by 2 and you get these smaller numbers, which are more convenient. I'm just describing all this for making a bot or making a calculator, but this is just you don't need to simplify at this part if you're making a solver, because once you have like a 100-digit number, it can't. That is simplified to a 20-digit number. You can't. You probably won't get more like complicated than that. Maybe by like 21, maybe, but likely not. Yeah. So, what was that now? So 8 and 25. What are they supposed to be? They're supposed to be the total amount of combinations in each of these. This is the true amount of combinations. So there's this happening. There are 8 combinations of this happening, and every 8 of those, there's 25 of this combination happening, which makes this that much more likely to happen. 25 divided by 8 times more likely to happen. This is like more than 3 times more likely to happen than this thing. So that's pretty important. This is like 3 times likely to be safe than to be unsafe, you know? And it shows up here, 24. What I'm doing here is adding every single combination. So we define this as like 8 and this is 25, and since now we're going back to the 3's here, there's 3 combinations of each. So 8 times 3, because this is a mine for 3 combinations and all 3 combinations are here. So we have a 24 right here. Let me give another example. How about this one, right? That is right here, and that is here, and that's here. So what's going on here? How many combinations are there each? The orange blocks, I kind of just leave blank because I know how many combinations are on each. So this 4's shore is, there's 2 mines in these 3 blocks. So there's 2 combinations where this is a mine, where this is a mine, and where this is a mine. And here there's only 1 combination where there's only 1 mine among these 3 blocks, meaning there's only 1 combination where this is a mine, 1 here and 1 here. Meaning there's 2 here and there's 1 here, so we add 2 of this and 1 of this. That is 16 plus 25, which becomes 41. 16 plus 25 equals 41. Do it. You can do it yourself and see it for yourself. So this is all the possibilities. It's not percentages. It's over 99 because there's total 99 combinations. We can look down here and see that I went with percentages this time. So 48 becomes 49, and what else? Oh, 75 becomes 76 if you do 100%. I should put decimals in here too, but they wouldn't fit in the squares nicely, I guess. So I just went with these numbers instead. But I can show you the decimal numbers too, I guess, if you want. And for the right side, I do the same thing. Is that there's a 6 and there's a 20, and then I divide that by 2 just to simplify. So every 3 combinations that are here, there's 10 combinations here. So this is more than 3 times likely to happen than this. It's kind of similar. Let's see, what was I gonna do? So let's just start with something simple like this one, right? And this one. There's only 1 combination where this is a mine, and it's this one, and that is 3. So just 3 here. And I did the same thing for everything else like that. A simple way to solve this, you see that there's only 1 mine among these 2, and I know that this is a 41. So that makes this a 58 because, you know, 99 minus 41. And I do the same thing here, and I do the same thing here, and I do the same thing here. That is these, and these. And so for example, I know there's only 10 combinations here. So this total should be 33 right here, because there's only 1 mine among those 2. So 33, 23, and 10. Another way to simplify calculating all this is that I know that there's 20 mines here, and there's 2 mines here. So the total among these must be 33 times 2, right? Because of the amount of mines. The total 33 is for 1 mine. So if there's 2 mines here, there has to be the total of each number has to be 66. The amount of combinations that is. So 20 minus 66 ends up with 46, and I know that these 2 blocks have the same probability of having a mine because they're just same. You just look here and they only do the same thing, I guess. That's what I'm saying. So you end up with 23 for both. You just divide 46 by 2, and you get these 2 numbers. All right, and of course the same thing. I just turn them into percentages, divide by 33, and you get these numbers. divide by 33 and multiply by 100. So 3 becomes 9. Is it here? 3 becomes 9. 20 becomes 61. 23 becomes 70. And you know, I narrowly avoided 69, I guess. So that's it. That's all your probabilities. This and the 24 up here, right here, the 24.242. Now we're not done yet, because I mentioned earlier about yield, right? That is a reward for clicking a block. So how do I describe this? If you click a block like right here, you could get like nothing. Like that's you just click that block and then it just gives you like a 2, and then you can't do anything here. I guess I should give you an example. Let's go with this one right down here. If you click this, and I'm lazy, so I just put numbers like up here. Here's the chance of there being 1 mine. Here's the chance of there being 2 mines, and here's the chance of being 3 mines. If there's a 2 mines, if you open this block, I need to use the box thing. If you open this and it says that there's 2 mines, then you have like no other clue. You know that there's 2 mines here, and there's 2 mines among these 3 blocks. There's like 1 or 2 mines here. This is more likely to be a mine than not. This is like I guess 33, and this is 66, I guess, chance of having a mine. And that's it. You have to guess again. So as I write here, I say dead end 100%. Dead end just means you can't solve more deterministically. You have to guess from there. That's really just what it means. Dead end doesn't mean you die. So let me give you an example with this. I need to draw a line here. Man, I just realized I didn't draw a line here. That's like kind of important. Not this though, right? Because this is kind of important. Actually, let me just. It's kind of important, so this is kind of important. Alright, so from here on, it's, I guess I should name this risk process. Wait a minute, this might lag a bit. Oh, it didn't. Okay. And that's what I call them. Alright, so up here, everything we did is to calculate the risk percentage, right? But now we solved the yield, which will give us a certain number, I guess. And then we just divide that by the risk, and we get the worth of clicking on making a guess on one of these blocks. So let's see here. We're looking at what would happen if we were to click this block. That is this block. I need to draw a box here. This block right here. And there are 2 numbers we can come up with. We can end up with. The simplicity of this is why I decided to use this box for the first example. So we can get a 4, or we can get a 5. That's because we know that there's 1 mine here. Alright, we know there's 1 mine here, 1 mine here, 1 mine here, and we know there's 1 mine here. And we know that if this is not a mine, which is we're gonna click, we're just assuming that this is not a mine, then this is a mine and this is a mine. So this is not a mine, and this is not a mine. So the only thing left among this this whole thing, since we know this, and this is a mine, we just need to know if this is a mine or not. And the number we get from clicking this will tell us if this is a mine or not. So we're taking both probabilities, 4 and 5, and we're seeing how far we can go with it. If we get a 5 here, and this is a mine, then dead end 100%. I should write that down. The text size is different. Oh well. just go along with it. So 100% chance of there being a dead end. from here you have to guess again, and I would assume this could be okay. This could be okay, but you might want to just forget this and just go to the other one, and that is this shore, and just make another guess. So this is kind of a bad, right? Everything here is bad. But if you get a green here, then it's pretty good actually. Your dead end chance is, as I calculated here, is 8.904%. That's pretty good. You have like a 91% chance of solving a bit more than what you have here. That is, if you don't get a 5, that is, you get a 4 or a 6, then this could be like both a mine or both not a mine. On the other hand, you also open this, which tells you for certain if this is a mine or not. And here we're assuming this 9% chance is when this is a mine, and then you're just blocked off, and you can't solve the rest of this stuff. And if you don't know how many mines there are here, then you're also blocked off from the rest of this stuff, and you can't keep going without making a guess. And you probably don't want to guess here, because at this point this would become a 50-50. This could stop being a 50-50, I guess, if you solve somewhere else, like right here, and go in from here. But right now it's a 50-50, so you don't want to guess here. You want to guess somewhere else. Or both of these could become mines, and then you're just stuck again if that happens too. I guess I should add that to the percentage. That's it's a bit more than that. So I show you a good example of something with a high yield, and coincidentally, it's the one that's with the lowest risk. Here I show you the chance of there being 1 mine, 2 mines, or 3 mines, and that is 1, 2, or 3 mines in these 3 blocks. I should probably do this. In the 3 red blocks here, that is, here there's 2 blocks and 2 mines, and here, if there's 1 mine among these 3 blocks, oh my god, I'm bad at drawing, among these 3 blocks, then we know that this is a mine, because there has to be 1 mine among these 2 blocks, and we know that this is safe. So that means we know how many mines there are among these 2 blocks. Yeah. And depending on what we get here, I guess we'll end up with a dead end anyway, and the same goes for here. So among the dead end chance we get, this is least likely, so it's kind of good. And it's also most likely to happen with a 52.8% chance. I also have a chance of dying here. So this totals to 100% right here, and among each of them you get like 100%, 55, 37.6. If you were to multiply all of this, like if you multiply this by this, and this, this is just leave it as is. If you multiply this by this, and you add it all together, right? Then you'll get the total dead end chance, which I didn't calculate, so you can do that for yourself. Anyway, so I said the yield process takes forever, and even a computer might not be able to do it. And I say that because I only calculated up to this point, up to the dead end point, But you can keep going. That is, you can make a guess depending on, let me just let's see what would be the best one to go with. Let's go with this one. If there's 1 mine here, and this box has a chance of giving you 1, 2, or 3. So now we have to copy it like this. And 1, 2, or 3, we this could be all green, or we don't know if there's a mine or not, or we know that both of these are mines. And for those, dead end chance is 100% and 100%, and here I don't know. I don't know yet until I check this whole thing. That is 3, 1, 2 here. I need to look somewhere else. Look at this. I would be able to go all the way here and clear all this. I know this is a mine. I know there's one mine here. And depending on the numbers I get here. Yeah, I would know how many mines are here. Oh my god, it would just get really complicated. So, I'm just leaving this as a question mark. But what I'm saying is, the yield process keeps doing this for every single combination until the whole board is solved for each and every single one of them, every single possibility, and that takes forever. Not here. Maybe a computer can do it in about I would say 1 minute, or maybe let's see. I would give it about 20 seconds. That is a long time for a solver, but that could actually happen. And for a really large board that is mostly unsolved, this could really take forever. So the yield process is something that I have a gist of, I have an idea of, but if there's no better way to simplify this entire process, then we're kind of screwed. We would need like a supercomputer to solve it. So that's it. That's everything I wanted to say about the whole risk and yield process of finding the best spot to guess. You compare the yield with the risk. That is all you do. And whatever block has the highest yield and the lowest risk gets clicked. That's really all it is. So with a computer, you can just estimate the yield, like how I'm doing it here, and then you take the exact risk and you just solve it. You know, the risk really takes not that long. I've seen the worst take like 1/10 of a second actually. 1/10 of a second. There's actually a calculator that shows you how long it takes to solve, and 1/10 of a second, it's really good. It's just about the yield process. That's gonna be the risk process multiplied by the amount of combinations, like the true amount of combinations. That's all like 100-digit numbers of the risk process. That's, oh man, how long is that gonna take? Wait a minute, I don't have to do it that way. So you subtract 7 digits. So this is a 7-digit number. If the true total amount of combinations, that is the one that is not simplified, is like more than 7 digits, right? You're gonna take a year. You're gonna take more than a year. You okay, let's say 9 digits, right? Just a bit. That's a bit better. If the total amount of combinations you have is like 13 digits, right? I'm saying I've seen some numbers go to 100 digits, but if you have a 13-digit amount of combinations in the whole board, then you'll take 1,000 years. So that's great, you know. Unless we get like a faster calculator, we can be like more efficient with this whole thing. So anyway, yield process. It's just maybe you want the computer to stop, like it can like loop this calculation for like 5 seconds or something like that. 5 seconds, 10 seconds, maybe 30 seconds if you want. And it'll just loop and it'll just get more accurate and more accurate, but then it'll just stop at a certain point, you know. I think that would be the best way to go about this. And another thing you could do is you can have a computer that learns as it makes these decisions. When it learns what's the best spot to click, it'll click it, and then it'll see the result, and it'll like collect the statistics, you know, and it'll realize maybe some spot is like better to click than others, and that's just my thought. I don't have any experience programming, so I don't know what it's like, especially the learning computer type programming. It's kind of, that must be pretty complicated. So that's all I wanted to say in this video. That's pretty bad. Honestly, it's pretty bad. I might want someone else to explain it, or I might get someone on Skype. That might be the best way to do it. I'll get someone on Skype with a bit of understanding for Minesweeper, and I'll just try to like describe this to them, and they can ask a question of what the heck I'm talking about. Sometimes I feel like I've been descriptive enough, but maybe I skipped something that I just thought I said. Nah, I'm not that stupid, or am I? I mean, I'm pretty stupid, but I don't know exactly how much. But so yeah, that's all maybe I'll make another video. This one maybe I'll leave it unlisted, or maybe I'll leave it public for like a week, or maybe like 3 days. I think 3 days is more reasonable, and then I'm gonna list it. Yeah, that's my thinking about it. So yeah, thanks for watching for this whole thing. I might want to get a better example. This is an example board that I thought is pretty good, but it's too simple. It leaves out certain probabilities. What do you call that? Certain situations when it comes to solving the probabilities of the board that's kind of important. Like, there's only 2 shores here, so we end up with opposite polynomials that are just the normal polynomials, like just upside down, you know? That's kind of dumb. That's way too simple. It's actually way more complex than that. So maybe I'll come up with a different example. Yeah, I'm gonna stop the video here. So thanks for watching.